Okay, M collection is a name for our new maintenance service. And the ultimate version of M collection service consists of 4 software, which are Civil NX, CIM, FEA NX, and the CAD ID. Civil NX is an upgraded version of MIDAS Civil with user-friendly interface and various API and plugin functions, which can overcome a lot of limitations from previous MIDAS Civil. We launched Civil NX beginning of this year, and we are in the process of developing powerful features ready for next year. CIM is special design tool as 3D modeler, especially for bridge structure, and it provides good connection with other softwares. And FEA NX is FEM software for more detailed analysis. Last but not least, CAD ID is the software used to generate drawing directly from CIM 3D model. When we have 3D modeler in CIM, then you can send it to Civil NX for global analysis and more global analysis, and you can send it to FENX for the more detailed analysis. CIM and they are interconnected together, so you can easily drawing into CAD. Another good thing is whenever you update your 3D modeling from CIM, your 2D drawing are automatically updated. So this is of M collection. Okay, so let us begin the webinar with our technician, Joseph and Rohit today. Joseph is Global Lead for CIM at MIDAS IT, and he will discuss about bridge modeling in CIM and drawing generation in CAD ID. Rohit is our technical support engineer, and he will take part for various features in Civil NX and FEA NX in analyzing PSC bridge. Okay, so in the course of the webinar, if anyone have any questions, there is a question box. You can drop any questions in the box so we can reply to your questions. And now I will pass the session to Joseph.
Thank you, Annabelle. Hello all. So welcome to today's webinar. So today's webinar is titled as All-in-One Integration PSC Box Bridge. So in the current scenario, when it comes to the bridge modeling and design, so one team, they will be carrying out the 3D modeling part, and another team, they will be carrying out the analysis and design part, and maybe the drafting or the BIM team, they will be carrying out the drawing generation part. So there is not much integration between the different teams or the different stakeholders who are involved in the same project. So now MIDAS is coming up with an innovative workflow in which we will be integrating all these aspects, that is the 3D modeling part, the analysis and design part, and the drawing generation part. So in today's webinar, we'll be seeing how we would be able to integrate all of this together so that we would be able to reduce the time required for the project and increase the efficiency and improve the accuracy in which the project is being done. So first, let's try to understand the agenda of today's discussion. So in this, first we'll be understanding the workflow, and then we would have a brief introduction to MIDAS CIM. Next, we would see a practical example in which we'll be carrying out the modeling of PSC box bridge in CIM. Further, the same model will be exported into Civil NX, where we'll be carrying out the analysis and design. And once we carry out the design part, then we will be creating the drawing, or we will be generating the drawings from the CIM model using CAD Infra Design. And further, we will be carrying out the localized detailed analysis using FENX. So this would be the workflow, or this would be the flow in which we will be carrying out today's session. So first, let's try to understand about the workflow. So in this case, first we'll be starting with the modeling in CIM. So you will be creating the geometric modeling of the bridge in CIM, and then you would be modeling the tendons, and then after that you would be modeling the boundary conditions, and you would be defining the construct stages. So once this is done, you would be exporting the CIM model directly into Civil NX. So now in Civil NX, you would be defining the loads, the load combinations, and then further you would be carrying out the analysis and design in Civil NX. So once you carry out the analysis and design, then you would be able to get the rebar data. So once you get the rebar data, then you will be modeling the rebar in CIM. And after that, you would be creating the drawing. So once you create the drawing, then you would be able to get the rebar annotation and the bar bending schedule using CAD infra design. And then finally, you would be creating the drawing sheets. So the final output in most cases would be the drawing sheets. So now you have completed the drawing generation part as well. And next, for detailed analysis, you would be exporting the parasolid model directly from CIM. And this parasolid model would be taken into FENX, where you would be carrying out the localized detailed analysis. So this is the workflow in which we would be integrating CIM, Civil NX, CAD infra design, and FENX, so that we would be able to achieve the entire integration between the different softwares. So next, let us have a brief introduction about MIDAS CIM. So first, let's try to understand the different capabilities of a CIM using this conceptual video. So you can directly import the geographical information into the CIM model. So it can either be the terrain or it can be the alignment of the bridge. So once you import the alignment, then you can directly assign the cross section to the alignment so that the 3D geometry of the particular bridge is modeled. So you can model all the members of the bridge using the different libraries. CIM is an alignment based software. So whenever you make any changes to the alignment, automatically the entire bridge shall be updated accordingly. You can parameterize the entire bridge. So based on the parameters that you enter, the bridge would be updated. You can also model the reinforcement and the tendons. Couplers and lapping can also be modeled in CIM. So based on the lapping properties that you enter, the rebar would be modeled in CIM. Extraction of drawings is effortless in CIM. The 3D model is dynamically linked with the drawings generated. So whenever you make any changes in the 3D model, automatically the drawings are updated. Detailed drawings can also be obtained directly from CIM. So all the construction documents or the drawings can be directly obtained from CIM, such as the plan, elevations, cross sections. You can also carry out the construction sequence animation, and the quantities of the bridge can also be directly extracted from CIM. Clash between different members can be carried out in CIM, and once you identify the clashes can be rectified in CIM. And finally, you can export the model into MIDAS Civil NX, where you can carry out the analysis and design. So thus, CIM is a one-stop solution which can be used by all the project stakeholders. So I hope that you have got a brief idea about the different capabilities of CIM. So next, let us try to understand how the modeling is done in CIM. The first step in any of the modeling would be creation of the materials. So now let us see how we can define the materials in CIM. So in CIM, we have an option called as materials. And under that materials, we have different options such as defining concrete, steel, rebar, etc. And over here, we have it database. So from the database, you can directly choose the materials. So in this case, first you'll be defining the concrete. And from the list, we can choose the different codes such as Euro code, American code, etc. So in this case, we are selecting Euro code. And for the superstructure, we are defining C4050 as a concrete material. And then for substructure, we will be selecting C3545 as a material. So you can see all the properties such as elastic modulus, Poisson's ratio, thermal coefficient, weight density, all of this is directly defined in CIM itself. So the advantage is that later on we can directly export these properties into MIDAS Civil as well. So now under the rebar, we have selected S460 as the rebar material. And next we will be selecting the tendon material, that is steel, from the drop down menu. And over here we are selecting the tendon material as Y177 S7 15.2 millimeters. So now we can see all the properties of this tendons. So next, if we go over here, you can see that all the properties of the materials that you have defined is visible under the data tab. So this is how we will be carrying out the material definition. Next, let us see how we can model the PSC box in CIM. In CIM, we will be defining each member as a library. So let us see how we can define the PSC box in CIM. So first, we will be creating a library. And in this case, we will be first creating the span 1. So the length of the span 1 is 34.9. So we will be defining the length. So once we have defined the length, next we will be importing the cross section. So now this is the cross section of the PSC box midsection. So we shall use the CIM user section command to define the cross section. So in this case, we will be first giving the name to that particular section. So in this case, we are giving the name as midsection PSC. And next we will be selecting the particular object. And once the particular object is selected, next we will be giving the base point. So now we are giving the top midpoint as the reference point. So now this is the preview of the PSC box section. Now we are saving this as a DWG file. So once we save this particular file as DWG file, then we can directly import that particular file into CIM. So next in CIM, we go to the user section command where we will be directly importing this DWG file. So next, let us see the preview of the file. So now over here, once you click on the modify option, you can see that this is the cross section that we have imported directly into CIM. Next, based on the length of all of this, we will be creating the different cross section. So similarly, we have imported the support section and diaphragm section. Now we are defining the different planes. So for example, when we consider PSC box, first we will be having the diaphragm section, then we would have the support section, then the tapering, then the midsection, right? So in this case, we will be defining the different planes according to the each cross section. So now we have completed defining the different planes. Next, we would need to define the path. So once we define the path, then later on we will be assigning the cross section to this path. So for that, we will be selecting all the planes to define the corresponding path. So now we are done with the definition of the path. Next, we would assign the cross section to this path. So for this, first we will be selecting the materials. So over here, we are selecting the C4050 material for the PSC box. And then first we will be assigning the diaphragm section. And in this case, we will be selecting the path at the extreme left end for assigning the diaphragm section. And once we click on the assign button, then you can see that this is the preview of the diaphragm section. Similarly, we can choose the next path and then assign the support section at the second path. So now we have created the support section as well. And then comes the important part, that is the tapered section. So now we have a tapering between the support section and the midsection. So we can use the tapered section option in CIM, and you can choose the section which shall appear at the start and the section which shall appear at the end. So in this case, we are creating a tapered section between the support section and the end section. So now in similar way, we shall carry out a modeling of the remaining sections as well. So now you can see that we have modeled the entire span 1 PSC box. In similar way, we can create different libraries for the span 2 and the blisters. So now we have created the libraries for the different span 1, span 2 and the blisters. Next, let us see how we can model the peer substructure. So we'll be defining the peer as a library. So now let us see how that can be done. So now we are giving the library name as peer. And then we'll be going to the user section. In this, we have already created a different user section for the peer cap, peer foundation and pile. So right now, under the user section, you can see that we have imported all the different user sections. Next, we will be creating the different members using the general member option. So in this first, we will define the material, that is C3545. Next, we would be assigning the peer cap top at the location. So using the 3-point method, we will be selecting the 3 points to create the plane of the peer cap top. And now once this is done, we will be using the tapered section option, and using the tapered section option, we will be defining the section that shall appear at the peer cap bottom. And now we are defining the height in which this particular section needs to be modeled. So in this case, we are modeling it to a height of 0.125 meters. And now over here, the variation which we are selecting is linear variation. So now the preview of this particular peer cap top is visible. Similarly, we shall model the remaining part as well. So in this case, the point to be noted is that we will be selecting a different variation between the different cross sections. So in this case, as we saw earlier, we are assigning the peer cap bottom first, and then as the end section, we will be selecting the peer cross section, and the height that we will be defining is 4.4 meters. And now over here, we will be selecting the variation, that is the shape variation, and we will be choosing parabolic shape variation. And now once we click on the preview, you can see that the parabolic shape variation is obtained for the particular peer. Similarly, we can model the entire peer using the same option. Next, let us see how we can model the foundation. For this, we will be using the concrete column option, and we will define the material, and then we can directly define the height. So in this case, the height of the foundation is 2 meters. And then from the database, that is the section type database, you can choose the different type of sections. So in this case, we will be choosing a rectangular cross section. So now we have defined a rectangle cross section foundation. Similarly, you can also define the piles using the same concrete column option. So in this case, we will be defining the pile height as 10 meters, and then the material as a C3545, and then the cross-section type we shall be selecting from this particular drop-down list. So we are selecting as solid round, and the diameter we are defining as 2 meters. And now we will be defining the location in which the pier needs to be, the pile needs to be placed. So now we have placed the first pile, and similarly we can place the second pile by defining the location. So now we have completed modeling the entire peer substructure. Next, we need to assign this particular peer substructure to a particular point. So we will be defining the point, and then we will be assigning the entire peer substructure to that particular point. So now we have completed modeling the entire peer. So in the same way, we can model the bearings also. So this is the bearing that we have already modeled in this particular case. So now we have completed modeling the PSC box superstructure and the peer substructure. Next, we will be assembling all the libraries that you have modeled. So now let us see how that can be done. So now we go to the assembly unit, and in this case, we will be defining the span of that particular assembly unit. So in this case, we will be defining the total span of the bridge as 79.9 meters. Next, as we saw earlier, we will be defining the planes in which we need to define the span 1 and span 2. And after that, we will be defining the path. So in this case, right now we are defining the path for the span 1. And next, we will be assigning the span 1 PSC box superstructure to that particular path. So now we have assigned the span 1 to the path. Similarly, we can assign the entire span to and the blisters according to the location. So now we have completed the superstructure part. Next, we need to define the location where we would be assigning the pier. So in this case, the first pier would be at the starting location. So we are defining the pier at a 0 location. And next, we need to assign the pier substructure at the particular location. So in this case, we'll be first selecting the point where we need to assign that particular pier. And then in this case, we'll be defining the location where we need to define the pier. So once this is done, you can see that we have assigned the pier at the required location. So in similar way, we can assign the bearings and the remaining piers. So now we have completed assigning all the libraries to the assembly unit. And next, we shall see how we can model the tendons in CIM. So in case of tendons, first we'll be modeling the anchorages. So we'll be selecting the anchorage option. And over here, either you can create the anchorages from the database, or you can customize the anchorage. So in this case, we will be customizing the anchorage. So as anchorage type, we'll be defining plate, and anchorage part we'll be defining as anchorage head, anchor head, and then we'll be defining the diameter and the height. So now we have defined the tendon anchorage. Next, we'll be defining the tendons. So first we need to select the reference member. So once we select the reference member, then we'll be defining the tendons. So we can define the properties of the tendon, such as the material of the tendon type, the strand diameter, number of strands, and the duct properties. So the advantage is that once you define the tendon properties, then this can be directly taken into MIDAS civil for analysis and design. And in this case, we will be defining the curve type as polygonal. And then we will be assigning the anchorage at the start and end of the tendons. Next, we will be defining the 3D coordinates. So we have the coordinates in Excel sheet. So we will be directly copying the coordinates, and then we will be directly pasting those coordinates directly into MIDAS CIM. So currently we are pasting the tendon coordinate values. So now we'll be clicking on the apply button. So once this is done, you can see that the entire tendons have been modeled according to the tendon coordinates. So this is how you would be able to carry out the tendon modeling part in CIM. Now we shall assign the assembly unit to the layout. So the advantage is that CIM is basically an alignment based software. So once you create an assembly unit, then when you assign that particular assembly unit to the alignment, the entire assembly unit gets updated according to the alignment. So let us see how to create the alignment and how to assign the assembly unit to the alignment. So in this case, right now we are going to the layout option, and under the layout option, we can define the plan under horizontal alignment and the vertical variation of the pier in the vertical alignment option. And you can also define the skew and the super elevation in CIM directly. So in this case, we will be defining a bridge alignment which is straight and which has got a length of 79.9 meters. And now we have defined the alignment of the bridge. Next, we can directly assign that particular assembly unit to this bridge alignment. So now we have clicked on the apply button. So now you can see that we have assigned the entire assembly unit to the alignment. So now we have completed the 3D modeling part of the bridge. In the next step, we will focus on creation of analysis case. So as a first step, we need to create a structure group so that we can create an analysis case later on. So now let us see how we can create a structure group. So in this case, we'll be going to the structure option, and in the structure option, we shall define the different structure groups. So the first group, it would be the substructure, then followed by the superstructure, and under the superstructure, we'll be having span 1 and span 2. So these would be the major structure group for this particular bridge model. So now we have completed defining the different structure group. Next, we need to assign the different members to the corresponding structure group. So we go to the option assign, and then we can directly select the structure group, and then we can directly select the members that needs to be assigned to that particular structure group. So currently we have selected the substructure, and then we are assigning the first PA members to that particular structure group. So similarly, by using the mouse cross-selection method, you can assign the different members to the corresponding substructure group or the structure group. So in this case, now we have completed assigning all the members to the corresponding group. So next, we will see how we can define the boundary conditions for this particular model. So for defining the boundary conditions, we have an option called as boundary. So we'll go to the model ribbon, and then we'll be selecting the boundary option. And from the drop-down list, you can define the different type of boundary conditions. So first we are defining the support. So you can give the degrees of freedom according to our requirement. And then we just need to choose the location where we need to assign the support. So in this case, we are assigning the support at the bottom of the pile. And next, we will be defining the elastic link. So over here, you can see that we can define all the properties, that is the stiffness properties of the elastic link. You can choose the units, and then you can directly enter the stiffness values in the elastic link property tab. So currently we are defining the different properties of the elastic link. So once you have defined the elastic link properties, then you can choose the starting vertex and the ending vertex where we need to define the elastic link. So in this case, we'll be defining the elastic link inside the bearings. So now we have defined the first elastic link, and now we are defining the second elastic link in the second bearing. So similarly, you can carry out defining the elastic link at the different locations. And next, we'll be defining the rigid link. So for defining the rigid link, you can directly select the member and the vertex. So in this case, we'll be defining a rigid link between the PSC box superstructure and the top node of the bearings. So now we have defined the rigid link. So you can see the red member refers to the rigid link. And similarly, you can define the rigid link between the bottom of the bearing and the top of the pier cap. So in similar way, you can carry out modeling of all the elastic link and the rigid link in the entire PSC box bridge model. So over here, you can see that this is the different boundary conditions that we have modeled in the second pier. So you can see the rigid link and the elastic link, and we have also modeled a rigid link between the bottom of the foundation and the top of the piles. So now we have completed defining the different boundary conditions. Next, we need to create the boundary group so that we can later on use it during the construction stages. So in this case, first we are defining the first boundary condition as substructure, and then we will be selecting the different boundary conditions that we have defined to this particular boundary group. So now we have selected those particular boundary groups, and next you can define the next boundary group. So in this case, we'll be defining the next boundary group as span 1, and then we'll be selecting the different boundary conditions as per our requirement. So you can use the mouse cross selection to select the different boundary conditions. So it is pretty much easier to select the boundary conditions. So now we have completed defining the boundary group as well. Next, we will be defining the construction stages in MIDAS CIM. So for defining the construction stages in CIM, we have a special option called as stage. So now let us see how that is done. So now currently we are in the construction stage property tab. So in this case, you can define the name of the construction stage. You can define the number of stages, and then you can also choose the duration of each stage. And then you can define or you can assign the different structure group that needs to be shown in the structure different construction stages. So over here you can define the duration and the dates. And next we go to the construction stage editor. So over here you can do the activation and the deactivation of different structure group and the boundary group. And you can also define the age in this particular dialog box. So over here we are defining the activation and deactivation of the 3 different structure stages. So we have defined 3 construction stages in our case, and then we are defining the activation and deactivation of each structure group and boundary conditions in this particular construction stage dialog box. So now we have completed defining the different structure groups. After defining the construction stages, next we need to create analysis case. So in CIM, to create an analysis case, you can go to the analysis option, and over here, these are the analysis lines of the different members. And then over here, you can select the different members, and you can also give the mesh size, and you can export the sulfate also. So we'll be selecting the construct stage analysis option, and in this case, we would be giving the length mesh as 1 meter, and we would not be exporting the sulfate in this case. So now we have created the analysis case, and once this is done, you can directly export this particular analysis case into MIDAS Civil NX. So now we have clicked on the apply button. So now Civil NX shall open up, and then you would be able to directly visualize the model. So now this is the Civil NX model that got directly exported from CIM. So now the analysis and design part in Civil NX shall be covered by my colleague Rohit Joseph. So I am passing the mic on to him. So Rohit, you can carry on.
Hello everyone, Rohit Joseph here. I work as a structural engineer at MIDAS. In this webinar, I'll be covering the global modeling of the PSC box girder bridge in MIDAS Civil NX and the localized detailed analysis of the anchorage blocks in MIDAS FEA NX. Moving on to the Civil NX part. MIDAS Civil, renowned for its global modeling, analysis and design capabilities, requires no introduction. MIDAS Civil NX is an upgraded version of MIDAS Civil, allowing the use of APIs and plugins. By opening the backend of the software to the users, MIDAS Civil NX enables them to overcome limitations previously encountered with MIDAS Civil through custom coding. The plugins are like apps in the Play Store for our phones, which will be developed by MIDAS or even by you, and it will be the answer for most of the engineering difficulties faced in this region. For example, last month we released few of the plugins which are developed specifically for the Hong Kong region. Towards the end of the session, we'll be discussing the latest developments in MIDAS Civil NX 2025 that are particularly beneficial for engineers in Southeast Asia. Moving on to the key topics. The first will be CIM to Civil NX model review. Second, time-dependent material properties. Loading, where we will be defining load cases, load groups, and assigning them. Construction stage analysis, where we will be reviewing the results as well. Moving load analysis as per Eurocode standards, defining reinforcements, and at the end, PSC design as per Eurocode. After the design, we will be giving the reinforcement details to the CIM team or the drafting team. Now, let us check out the analytical model imported from MIDAS CIM to MIDAS Civil NX. Let's check out the workstream menu and let's start from the top. The first part is the elements. We have defined everything as a beam element in CIM, and this has been imported directly to Civil NX. We can turn on the transparency feature, and here you can see that only the sections have been imported and the anchorage blocks has not been considered as a structural element. So these are just the sections. Now coming on to the properties, we have the material and the section properties which was defined in CIM. The first one is C4050, which is the superstructure properties. So the standard is ENRC and maybe C4050, which was as defined as that in CIM. Scrolling down, we can see C3545, which is the substructure elements, and Y1770S7, 15.2 mm, which is the tendon property. It's a steel material property. Scrolling down the sections, let's click on the midsection PSC, right click, properties. So these are the section properties which has been taken directly from CIM. Even though they are all user-defined sections, we don't have to take the sections to section property calculator, but it can directly be taken directly from CIM. But here we'll have to check on these options, consider shear deform, and the auto options for the shear checks. Click on OK.
So likewise, we have different sections which have been imported from CIM. The pier cap top, which is the tapered section, as you can see here. Right click, properties. So this is the tapered section. And the pier column, properties. It's a user-defined section which is having a curvature at the edges. So again, I'll check on the consider shear deform in this case. Click on OK. Scrolling down, you can see the tapered sections. There are a lot of tapered sections involved in this model. So all these things will be automatically taken directly from CIM. Now the boundary conditions. Let's turn on the boundary conditions. Right click, boundary. So the rigid links, elastic links, and the support conditions defined in CIM will be taken directly to Civil NX. So at the bottom, I have fixed it, and here I've given a rigid link for connecting the pier column with the pile cap. Scrolling up, you can see the bearings, which is connected to the superstructure with the help of rigid links, and again the bearing bottom is connected to the pier column with the help of another set of rigid links. So likewise, all the three connections have been defined. Now the tendon property, right click, properties. So this is a tendon property which we have defined in CIM. The tendon type is internal, post tension, the material ID6, the total tendon area is 0.004935 and duct diameter 0.1. The relaxation coefficient is European. So rest of the things we have taken directly from CIM. Click on OK. Now the tendon profile display. So the tendon profile coordinates have been taken directly from CIM to Civil. Moving down, the construction stages. So there are three construction stages which we have defined in the 3D model CIM. Right click, properties. So here the element and the boundaries are already done in CIM and that information has been passed on to Civil NX. The first one is the substructure along with the age, which is activated. Now the boundaries are also activated. Now the load is remaining, which is something we have to define in Civil NX. Let's check out the construction stages. So in the first construction stage, only the boundary conditions and the substructure elements are activated. You can see the supports, the rigid links, and the bearings activated. The next construction stage, the first span and the pre-stressing has been activated. In the third construction stage, the second span along with the pre-stressing tendons have been activated. Now, let us start by defining the time-dependent material properties of concrete. In this example, I'll be considering the time-dependent effects of concrete only in the superstructure elements, that is grade C40-50 concrete. For defining the time-dependent effects, go to properties, click on time-dependent, creep and shrinkage. First, let's define the creep shrinkage effects. Creep shrinkage. The code chosen will be European. The characteristic compressive strength of concrete is 40,000 kilonewton per meter square. The relative humidity, I'm going to take it as 70, and the notional size of member, I'm going to consider it as 1 for the time being, just for visualization of the graph. The type of cement, class N. The type of code, EN 1992. Second, for concrete bridges. Now, the age of concrete at the beginning of shrinkage, I'm going to take it as 3 days. Let's see the results. So this will be the graph for notional size of the member 1. Likewise, for the shrinkage strain, you can see this is the graph and varying with respect to time. Close, click on OK. Likewise, let's define the compressive strength of the concrete. Click on add, compression, compressive strength. The code chosen should be European. And here we have to give the mean compressive strength of concrete at the age of 28 days. As per the code, I'm going to give the value of 40 megapascal plus 8 megapascal, that is the standard deviation. So here it is going to 48,000 kilonewton per meter square. So this will be the graph varying with respect to time and compression. Click on OK. Now let's link these properties with the material. For that, let's go to material link, choose the functions for creep and shrinkage and compressive strength. I'll be choosing C40-50 grade of concrete and click on add. Now For calculating the nozzle size of the members, click on Change Property. Here, the auto calculate. The code chosen will be CEB FIB 2010. We have the standard Japanese code as well. So here, this will be the formula that will be used to calculate the nozzle size. I'm going to choose the elements and click on Apply. Now the nozzle size of all the members are calculated. And accordingly, the time-dependent effects of concrete will be assigned to each element. Coming on to the loading part. Just like in MIDAS Civil, it is a three-step process. First part is defining the static load cases. Second is creating the load groups. And finally, assigning the loads corresponding to different load cases and load groups. Let's start by defining the static load cases. For creating the load cases, click on Load, Static Loads, Static Load Cases. We need 4 different static loads. Self-weight. The type of load should be construction stage load since it is activated in the construction stages. And likewise, pre-stress for the pre-stressing. SIDL for the SIDL loads. CB, that is for the crash barrier loads. Again, it is a construction stage load since all these 4 loads are activated in the construction stages. Now, coming on to the load groups, click on Group in the workstream menu. Load group, right click, New. We need 5 different load groups. Self-weight, for activating the self-weight, click on Add. SIDL, for grouping the SIDL loads. Crash barrier loads, CB, click on Add. And 2 pre-stressing, since pre-stressing is activated as in 2 stages. PS1, Add, and PS2, Add. Now, let's assign the loads. First, static loads. Sorry, self-weight. Load, self-weight. The load case name is self-weight. The load group name is self-weight. And EZ component is -1, that is in the negative vertical direction or gravity direction. Click on Add. Close. Let's turn off the hidden view. Beam loads. Element. The load case name is SIDL. The load group name is SIDL. It's a uniform load in the global direction -20 kilonewton meter. Now I'll select the elements. I'm just selecting the superstructure elements. Click on Apply. Now, likewise, the load case name is crash barrier. CB will be the load group name and it will be having an eccentricity in the global y direction. The eccentricity is -4.85 meters since crash barrier loads will be assigned at both the sides of the girders transversely. Coming down, -10 kilonewton meter. Click on Apply. You can see the loads activated here. Likewise, in the other direction, 4.85, click on Apply. If I turn on the hidden view, you can see that the crash barrier loads are applied at both the sides of the girders. Now, coming on to the pre-stressing. Go to Load, Static Loads, choose Pre-stress. The tendon property is already defined here, which we have exported it from CIM. The tendon profiles are also defined, which is again exported from CIM. Now, applying the tendon pre-stress. So here, the load case is pre-stress. The load group name is PS1. First, I'll choose the first set of tendons, B1, B2, B3, B4. Scrolling down, T10, T11, T1. So these tendons are selected. Now stress. I'm going to change the units. Newton meter. I'm going to give tendon pre-stressing of 1350 Newton per mm square. Grouting after, I want the grouting to be done in the same stage. Click on Add. Likewise, I'll be choosing the remaining tendons. So B1, B2, B3, all these things are already defined, starting from B5, sorry. Scrolling down, E22, E8. The stresses are same. Click on add. Now the pre-stressing forces are also activated. Now let's activate these forces in the construction stages. Now coming on to the construction stages. In CIM, we have already defined 3 different construction stages and we have activated different structure groups and boundary conditions. So you can see here CS1, CS2, CS3, and in each groups we have activated the structure group as well as the boundary group, but the loads were not defined in CIM. So this information has already been imported from CIM. Now let us activate the loads which we have defined in the previous step. So now click on CS1. Going on to the load, I'll activate the sulfate on the first day. Click on apply. Likewise, in the second construction stage, I'll be activating the first pre-stress. Click on apply. In the third construction stage, I'll be activating the second set of pre-stressing. Click on apply. Now we need a fourth construction stage for capturing the long-term effects of concrete, that is creep shrinkage effects. Click on add. CS4, duration is 10,000 days. I'll be activating SIDL and crash barrier on the first day. Click on OK. So now you can see all the loads has been activated in the construction stages. Close. Now going to the analysis control tab, click on construction stage analysis control and add. So here I'll be separating out SIDL and crash barrier loads. Click on OK. Likewise, crash barrier. Click on OK. Click on OK. Now the construction stages has been defined. We can activate the boundary conditions and also the tendon profiles. Click on OK. So in the first construction stage, only the boundary groups and the substructure is activated along with sulfate. In the second construction stage, the first span is activated along with the tendons. So you can see these are the tendons. If you want, I can include the transparency feature here. You can see the tendons passing through and also the rigid links. Now in the next construction stage, the second span is erected along with the second set of pre-stressing. And in the third construction stage, the crash barrier and the SIDL loads are activated, as you can see over here. Let us run the analysis. Now the construction stage analysis is completed. Let's go to the first construction stage. Let us check the bending moment diagrams, results, forces, beam diagrams, summation. First, let's check the dead load. We don't have any bending moment here since it is just the sulfate. We can activate the legend as well. Now checking the axial forces, you can see the axial forces due to sulfate. In the next construction stage, the first girder is activated. Now let us check the bending moment, My. See the bending moment diagrams here. The pre-stressing is also activated. So tendon primary, this will be the tendon primary forces, and the bending moment you can see from the legend. Tendon secondary, you can see because of the secondary effects of the tendon, the forces are transferred to the substructure. Now the third construction stage, this will be the tendon secondary and this will be the tendon primary because of both the tendons activated. Now in the fourth construction stage, we can see the effects due to creep secondary and shrinkage secondary, the summation forces. So you can see all the forces minimum diagrams here. We can also check the deformations, displacement contour, summation. You can see this is how the summation look like, and this is how it is going to deform. Tendon primary, it is going to deform upward, as you can see here, due to the effect of tendons. Moving load analysis in MIDAS Civil NX is a three-step procedure. First, go to load, moving loads, and choose the appropriate code, Eurocode. And the first part is defining the traffic lanes. Click on traffic line lanes, click on add. We need three different traffic lanes and one lane for remaining area. First one is L1. The lane width is 3000, eccentricity is minus 3 meters, and the wheel spacing is 2000. Eccentricity, I'm not going to consider any eccentricity here. Traffic lane optimization. Allowable width is 3000. When this option is checked on, the software places the vehicle at three different locations in a single lane transversely, at the left, at the center, and at the right. And the vehicle position which is yielding the most critical results will be displayed. Now the vehicular load distribution, I am choosing it as a lane element since it is a beam, single beam model. And if it was a PSC composite or a grillage model, we should have chosen cross beam. Now the points. Okay. Likewise, we have to create for L2. Eccentricity is 0, lane width is 3 meters, wheel spacing is 2 meters, transverse lane optimization checked on. The vehicular distribution is lane element, points. Now the remaining area. Lane width will be 0.6, that is 60 mm. Eccentricity will be 4.5. Wheel spacing will be 0. Transverse lane, we don't have to check it on, points. Now the lanes have been defined. You can see the lanes L1, L2, L3 and the remaining area. Now let's define the vehicles. Click on vehicles, add standard. So you can find all these standard vehicles. So the first one is load model 1. You can see all the values as per the Eurocode standards. I'm choosing load model 1. Click on OK. Likewise, click on add standard. I'm going to choose load model 3 UK national annexure, and I'm going to choose special vehicle 196. Click on OK. So you can see all the vehicles as per the Eurocode standards. Okay. Now let's define the moving load case. Moving load case, add. I'm going to just define one load case. So here, click on LM1 and 3 multi-straddling. Choose load model 1, and the special vehicle will be load model 3 UK national annexure. I'll be choosing all the lanes here, and the remaining area will be taken to this side. I'm not going to consider any straddling. Click on OK. Now moving load analysis, defining all the loads, vehicles and lanes have been completed. Now let's run the model. Now the analysis is complete. Now let's check the results. Set all loads, click on OK. Go to results, forces, beam diagrams. can see three different load cases here: MV max, MV min, and MV all. So MV max displays all the sagging moments. It's an envelope case which displays all the positive moments. For defining the rebars in a PSC section, go to Properties, Section Manager, Reinforcements. So here I'll be defining the rebars for midsection, which is the section that I'm going to design for this session. So click on midsection, and at the top you can see longitudinal and shear reinforcements. First, let's define the longitudinal reinforcements. Same rebar data at I and J end, coordinates, and the guideline which ensures the cover. So I'm going to give a cover of 60 mm. The I and J end, the type is line. The input method I'm going to choose is B. So the starting point and the end point. The center to center distance between the bars is 200 mm. And I need the edge bar, which is the closing bar. And the diameter of the bars will be taken as 20 mm dia bars. So now first click on the starting point. Click on the points and add. Likewise, we have to define the rebars for the rest of the section. So now we have defined the longitudinal rebars. Going on to the shear reinforcements, click on shear reinforcements. I'll be defining the diagonal reinforcements and the torsional reinforcements. First, the pitch. I'll give a pitch of 0.15 and the angle as 90 degrees. And clicking on here, I'll be choosing 12 mm dia bars and number will be 4. Click on OK. Likewise, for the torsional reinforcement, the pitch will be again 0.15 and AW is going to be 110 mm dia bars, P10, and I'm going to give 1. Click on OK. Likewise, P12, and that will be 62. Click on OK. So now we have defined the shear and the longitudinal reinforcements. Coming on to the design of the PSC section, I'll be designing a single element number 79, which is present at the mid of the second span. As you can see over here, this is the element number 79. And first, we have to create the load combination. For creating the load combination, click on Results, Load Combination, choose Concrete Design. And in this part, I'll be choosing auto generation, but we also have other options where you can input the load combination in a spreadsheet format. But for now, let's go to the auto generation. Choose Eurocode. So I want to consider all these for the design. I'm going to choose rail traffic. Click on OK. Now you can see all the load combinations have been created. Since we have only defined construction stage loads and moving loads, the load combinations are very less. So you can see over here. Now, going on to the design, PSC design, choose Eurocode, design code option, Eurocode. So these are the input parameters that we find. The national annexure, I'll be choosing recommended. So now, the pre-stressing steel type, smooth bars and wires. Now the output parameters, click on select all. So for the ultimate limit state, I want the design for bending resistance, shear resistance and torsion. Likewise, for the serviceability limit state, I want the stress for cross section at a construction stage, stress for cross section at service load, principal stress at a construction stage, principal stress at service loads, tensile stress for pre-stressing steel, and crack control. All those serviceability limit checks should be carried out. Now click on OK. Now for the design parameters, you can see service load combination, the quasi-permanent, characteristic and the frequent. All the load combinations are segregated out. Coming on to the short-term load combinations. So here I have not defined any long-term load combinations. If you want, we can do that as well. Coming down for the exposure class, we can provide the exposure class here and the shear connectors, which is not required for this case. Modify material. Click on C4050. As you can see, we can modify the concrete material property here to C4050, and the rebar code is ENRC, and the grade of main rebars and the sub rebar used is S460. We have different options for that. We have S500 as well. Likewise, for C3545, this will be the grade of concrete and the rebar grade, which is selected. Now, design position, I'll be designing element number 79. Likewise, for the position of the PSC output, this will be the output position. So 79 is the element under review here. Let's click on perform design. As you can see here, the design is already completed. We can click on the Excel report and check out the PSC design report, which is generated from the software. Yes. Now we can see a very detailed PSC report. The design code is Eurocode. Element number is 79 and the position is I end. The condition, as you can see, all the conditions and the partial safety factors which is used for the design is specified here. Section information, material information, tendon profile information, the ultimate moment resistance, the positive moment. As you can see here, the neutral axis depth calculation is being carried out. Since it is an iterative process, each iteration and the values which we are getting is displayed here. Coming down, the maximum moment is compared with the section capacity, and it turns out to be okay. Likewise, the negative moment is also checked. First, neutral axis depth is calculated, which is again an iterative process. Coming down, since it is not having any negative moment, it is 0 here. Shear resistance. So this will be the load combination which is giving the maximum shear, CLC, CB1, and the design situation is persistent and transient. The load combination type, the capacity and the demand of the section can be seen here. Scrolling down, the shear capacity is calculated and it is checked okay. Likewise, coming down, the minimum shear requirements, you can see all the checks criteria has been satisfied. Scrolling down, the torsion resistance. So the maximum torsion resistance is observed for this load combination CL-CB2. As you can see over here, the torsion resistance is being calculated. I'm not going into depth for this. So here, transverse reinforcement is not required. Scrolling down, maximum torsion moment, which is compared again with capacity. Now, for the service states, stress check at transfer and during construction. So for each construction stage, it will be checking for the most critical stress conditions, and the critical stage is CS3, that is the third construction stage, and you can see these are the stress limit values, and it turns out to be okay. Scrolling down, which is for the service load combination, the girder, compression. Now, likewise, a very detailed report is generated for element number 79 as well. Now for the bending resistance, you can see everything in tabular format. The shear resistance, the torsion resistance, the stress at construction stages for different construction stage. And in this, it is the CS3 is the most critical construction stage, and you can see the stresses at this construction stage. Now, the principal stresses at service limit, the tendon stresses, which is after all the losses, you can see the tendon stresses as well. So this is how we can design a section in MIDAS Civil NX.
After design, we have the rebar details, which will be used in CIM to model the rebars and generate the 2D drawings. Over to Joseph.
So thank you, Rohit. So now we have got the rebar data. Next, let us see how we can model the rebars in CIM. So for this, first we'll be going to the library where we need to model the rebars. So in this case, we'll be going to the span 2. And next, we will be selecting the member in which we need to model the rebars. So currently, we will be selecting the required member. And then we will be selecting the plane where we need to model the rebar. So now this is the plane in which we will be modeling the rebars. So we have different options for modeling the rebar. So in this case, we will be using the select member edge option, and you can define the properties of the rebar in the property tab, where you can define the material, the diameter of the rebar, the bending radius, the cover thickness, the hook details. So all these properties can be directly entered in the rebar property tab. And then based on the properties, the rebar would be modeled. So now in this case, first we'll be modeling the transverse rebar. So right now we will be selecting the edges in which shall act as the reference to the transverse rebar. So now you can see that we have modeled the transverse rebar, and next we will be modeling the longitudinal rebar. So over here you can see that we are defining the properties of the longitudinal rebar. So you can also define the spacing of the longitudinal rebar as well. So in this case, we are giving a spacing of 200 mm center to center. And now we will be selecting the transverse rebar as reference for modeling the longitudinal rebar. So you can keep the longitudinal rebar above or below the transverse rebar using the reverse direction option. So now we have modeled both the transverse and longitudinal rebar at that particular location. Similarly, we can model the entire transverse and longitudinal rebar at that particular location in CIM. So now we have completed that. Next, we will be arraying this particular rebar to the plane according to our requirement. So in this case, we will be first defining the spacing in which these rebars needs to be arrayed. And then next we will be selecting the members in which this rebar needs to be arrayed, and we will be selecting the rebars which needs to be arrayed. And after that we will be selecting the plane until which we need to array this rebar. Next we'll be clicking on the apply button. Then you can see that the rebar would be arrayed, and then now we have created the entire rebar for the particular members. So now you can also visualize the rebar cage by hiding all other members. So now this is the rebar cage that we have modeled. So it is quite easier to carry out the rebar modeling in CIM. So next let us see how we can carry out the drawing generation part in CIM. The drawings can be directly generated using CAD infra design. So CIM is dynamically linked with CAD infra design. So next let us see how we can generate the drawings. So for this we go to the drawing view option, and then we will be creating the drawing view according to our requirement. So in this case, first let us try to see how we can create a cross section directly in CIM. So in this case, by just adjusting the arrows, you would be able to create the drawing view. So now this is the drawing view that we are creating, and now you can adjust the depth or the view depth of the particular drawing view. And after that, so now we have created a drawing view, and next let us click on apply button, then automatically MIDAS CAD infra design shall open up. And then you would be able to see the drawing that we have created. So you can see the geometry of the concrete, the rebars, and the tendons. So in CIM, we also have an option called as auto dimension. So the auto dimension option that is used to automatically annotate all the concrete dimensions directly in the drawing. So you need not do the manual dimensions anymore. So over here at the left bottom, you can see that there is an option called as auto dimension. So once you create the drawing view, you just need to check on this particular auto dimension option, and then automatically in the drawing, all the dimensions, all the concrete dimensions would be labeled. So now you can see that the dimensions have been labeled directly in the drawing, and you can merge any of the dimensions using the DC command. So you can customize these dimensions as well. So this shall save a lot of time for the drafting team. So now we have completed the dimensioning part using the auto dimension option. And next, let us see the creation of another view, that is the plan view. So for this, we take an option called as 3-point view. So in this case also, we would be directly creating the views using these arrows. So next, we can move the direction of the location of the plane according to our requirement. So now we have created the plan view. And now this is the plan view that got generated in CAD Infra Design. So in this, you can see the concrete geometry and the tendons and the rebars. So you can uncheck the members that is not required. So in this case, we have removed the tendons and the rebars from the drawing. So this helps us in customizing the drawing according to our requirement. And next, let us try to extract a elevation drawing from this particular model. So for this, we use the by curve option. And now we have selected all the members. And once this is done, you can directly extract the elevation drawing directly from the 3D model. So this is an example of how we can create the different drawing views. Next, let us see how we can annotate the rebars. So in this case, you can use the rebar annotation option, and you can directly get the annotation of the rebar. So in this, element refers to the name of the rebar, D2 refers to the D20 refers to the diameter. Then we also can get the number of rebars and the spacing and the shape of the rebar. So we can customize this rebar annotation as well. And next, using the rebar schedule, you can directly extract the bar bending schedule. So you just need to choose the particular drawing view. And once that is done, then you shall directly get the bar bending schedule in the drawing with just a single click. So now you have obtained the bar bending schedule. So over here you can see the bar mark name, the diameter, the rebar shape, the length of the rebar, the weight of the rebar. So all of this data can be directly obtained within a single click. So next, let us see how we can create a drawing sheet in CAD Infra Design. So for this, we are currently using the templates which are available in CIM. And so we are selecting MIDAS sheet A1, and we are selecting the scale of this drawing as 1:100. So you can also import the template of your company to create the drawing sheet. And you just need to drag and drop the drawing view into the sheet. So currently we are dragging and dropping the different views into the sheet. And next, if you want to change the scale, you can just select the boundary box, and then you can change the scale of that particular drawing view. So now we have edited the scale of that particular drawing view. And now you can move this particular drawing view according to our requirement. And similarly, you can drag and drop all the other views into this particular sheet. So now let us see how that is done. So now we are placing the plan view and changing the scale of that. And similarly, we are going to do it for the same for all other drawing views. So now we are done with placing all the drawing views. And next, finally, we will be exporting this particular drawing as DWG file. So we have an option called as save as DWG. So you can directly save this particular drawing in DWG format, and then you can share it with the contractor or the clients. So now we have seen how we can carry out the drawing generation part. Next, let us see how we can export the parasolid model from CIM into FENX so that we can carry out the localized detail analysis. So from CIM, first you need to choose the members that needs to be exported into FENX. So in this case, we will be selecting only the members which we have already modeled the rebars. So currently we'll go to the CIM logo and then we'll click on the export and then we'll choose the parasol option. Next, we would select the members that needs to be exported into FENX. So we will be selecting the concrete geometry and then the tendons and the rebars. So now we have selected the members that need to be exported. And once we click on the apply button, then we can save this particular file as a parasolid file. And once this is done, you can directly go into FENX and there you can import this parasolid file. So now we have imported the parasolid file into FENX and you can see that we have imported the concrete members, the tendons and the rebars. So next, my colleague Rohit, he shall be explaining about the advanced analysis that can be done using the FENX.
Now, coming on to the MIDAS FENX part. As we have mentioned before, MIDAS FENX is an advanced finite element analysis tool tailor-made for civil and structural engineering applications to perform more refined finite element analysis. In the bridge industry, MIDAS FENX is essential for complex geometries like anchorage blocks, diaphragms, and its advanced solver and analysis visualization is used by many engineers to prove structural redundancy. Its ability to perform nonlinear analysis, dynamic time history analysis, geotechnical analysis, concrete cracking analysis, and more allows for in-depth and highly accurate analysis. In this section, we'll be importing three segments of the bridge, including the anchorage blocks, into FENX from CI to analyze crack propagation under sulfate and pre-stress. The agenda for this part of the session will be first, the importance of detailed analysis, followed by CIM to FENX geometry input, material and property, automation feature, constraints, where we'll be discussing how we can simulate the global stiffness since we are just modeling a part of the entire bridge, followed by loading, where we deal with sulfate and pre-stress, generating nonlinear analysis load case, and finally, analysis results review. Importance of detailed analysis. As engineers, we strive to keep things simple to better understand our models. But do we really need a final localized analysis? Complicating matters much. Already it's too complicated in our segment. So I have listed a few of the structural failures in our sector. The first two, which is more relevant in concrete bridges, crack propagation in diaphragms and anchorage block location, concrete spalling and bursting of reinforcements. So it has been observed that during construction stages or in the service stage of pre-stress concrete bridges, cracks often begin to propagate near the anchorage blocks and diaphragm locations, which is primarily due to stress concentration and something that cannot be effectively diagnosed using beam model. And in most of the cases, we don't usually model the reinforcements. So yielding of reinforcement is also something that cannot be diagnosed. The next one is mostly specific for steel bridges. Localized structural component failures, web buckling. So in steel composite bridges, we model the steel eye girders as beams in most cases. During early construction, where the slab is not activated, web tends to buckle under wet concrete loads and often causes failure due to insufficient transverse stiffness. Now, this scenario can be captured only in plate or solid models and cannot be diagnosed using beam or truss models. Inaccurate soil structure simulation. In Southeast Asian countries like Singapore, where the soil is weak, soil structure interaction significantly influences design forces. Modeling multilinear soil springs often is insufficient to replicate the exact site conditions, and hence modeling the soil itself is always recommended. Overestimation of joint stiffness. Now let us take a simple case of peer to superstructure connection where most of us we use rigid links, which is having infinite stiffness to simulate that connection. And this is something which is unattainable in practice. To illustrate this, I have compared the stresses and deformation in the following truss structure. So to your right, you can see this is a truss structure where I have not modeled any joints, and to your left, to your right, sorry, you can see the truss structure where I have modeled two of the joints, as you can see here. It has been observed that in the truss model, the displacement and stresses are underestimated, 29 and 28%, compared to the localized zone model, where the displacement is 4.389 centimeter, which is much higher than 3.395 centimeter. Likewise, the stresses, which is 32 megapascal, and in the other case, it is 25 megapascal. Thus, we can conclude that localized analysis is essential to accurately simulate structural behavior in most of the real world scenarios. Coming on to our case. So we have already modeled the bridge in MIDAS Civil NX, where all the elements were modeled as a beam. We have not modeled any anchorage blocks there. The model converges perfectly and we are getting desired structural behavior. Stresses and deformations are within limits and the elements under review passes the design checks. Now let's do a more localized analysis in FENX. For that, we'll be taking just three box girder elements, which will be modeled as solids. Tendons and rebars will be modeled as embedded truss elements, and metal nonlinearity will be taken into consideration for concrete to understand the crack propagation.
Before diving into our model, I forgot something. So I would like to briefly discuss two project applications of MIDAS FENX where our clients found the tool particularly useful. One involved the construction of a metro bridge with several simply supported spans. The design had been approved and the contractor was proceeding with rapid construction. However, after 6 spans were completed, cracks began to appear in the diaphragm of the first span. In response, a 3D model with reinforcements was quickly developed in MIDAS FENX, and based on the analysis, it was determined that these were merely surface cracks. Construction resumed only after this was confirmed. Now, next is a balance cantilever bridge that began showing cracks 6 months into service. The engineers revisited the design and confirmed that the global line model revealed no issues. Consequently, they created a 3D solid model to validate their assumptions. This analysis revealed higher stresses caused by the blisters on the top and bottom slabs being too close to each other, a detail which no global line model could predict, caused this issue. Based on the FENX results, the bridge was retrofitted. So these examples highlight the importance of localized analysis to accurately simulate the structural behavior in real life scenarios. Now let's move on to our case. Geometry export in MIDAS FENX. MIDAS FENX offers a wide range of options for creating 3D models. Geometries can be directly imported as parasolid files from any BIM platform like CIM. Complex geometries, such as those shown in the figures below, can be drawn in AutoCAD and imported into FENX. Alternatively, models can be created directly in FENX using conventional tools like Extrude, Sweep, and others. Additionally, models or part of models can be imported from other MIDAS family software such as CivilNX or GEN. For instance, if we have a truss bridge in CivilNX, the joint information can be imported directly into FENX and modeled as a solid or plate for detailed fatigue analysis. Now, moving on to our case, let us once again review the process of importing CIM geometry into FENX as demonstrated by my colleague Joseph in his last slide, along with the additional modifications made to the geometry to make it suitable for our analysis.
Let us start by importing geometry from CIM. So for that, go to File, click on Open. So here, choose All Files and click on the CIM Parasolid Export file. Open. Now we can see that the three segments has been imported, the geometry,
and the tendons, the anchors, the anchorage blocks, and even the rebars have been imported. So for example, if you want to see the rebars, let's check on good solids. I'll give some transparency to it. Transparent. You can see the rebars and the tendons going on. Now we have to make some changes to the model so that it becomes walkable. So first, go to template, translate, and translate it. Yeah. The next part is deleting the unwanted elements. For example, I don't want to consider these blocks, so I'll just select them on the.
Now let us define the material and properties. For the girder, the sphere crack concrete material model will be used to capture its crack behavior. Linear steel material properties will be assigned to the tendons and rebars. The girder will be modeled as a solid element, the rebars as embedded truss elements, and the tendons as tendon elements. Now, let us move on to the software.
Now, let us define the material and properties. For defining the material properties, go to Mesh, Material, click on Create Isotropic. Now, the first one will be concrete. Model type is concrete smear crack for including the nonlinear material properties of concrete for understanding the crack behavior. Now, click on DB, choose ENRC as a standard. DB is 3545, which is the concrete grade for our superstructure. Click on OK. Now, nonlinear material properties, the tension function, click on this icon. Now, for the tension function, I'll be choosing orbit, and the FT value will be 2 Newton per mm square. EF will be 0.08, and H value will be 100 mm, which is the mesh size. Click on apply. Choose tension function. Likewise, for the compression function, click on this icon. I'll be choosing parabolic, and FC value is 35. GC is 44.612, The H value will be 100 mm. Okay. Use compression function. Likewise, for the shear function, we found the 3 dots and the value is 0.01. Click on OK. Choose shear function, and the stiffness will be considered as secant. Click on average radius. This value I'm going to use 10 mm. Okay. Likewise, create material properties for rebar and tendons. Here, rebar. The model type is elastic. Now click on the DB and choose steel. Standard is ENO5S, and I'm going to choose S450. Click on OK. Click on apply. Likewise for the tendons. The model type is elastic. Click on DB and type is steel. Standard will be ENO5 and the material will be Y1670S7 and click on OK. Likewise, we have to define the property. For defining the property, go to Mesh, Property, click on 3D. The first one will be for the girder. Complete. The material is isotropic. So initially, I should have defined it as concrete. Click on OK. So now it's concrete. Click on OK. Likewise, 1D. This is for the rebars. I'm going to choose embedded truss elements. Rebars. The material is rebar, and the cross-sectional area should be 805 mm square. That is for 32 mm dia bars. And click on section. Section can directly get the values from here. Click on solid round, and I'm giving 32. Okay. So okay. Now, likewise for the tendons, 1D, and I'm going to choose tendon. So this is same as embedded truss elements, but when you choose tendons, we can add the tendon losses, and all those effects can be carried out if we are going for a construction stage analysis. So here, the material should be tendons, and the total tendon area is taken from the civil, that is 1875.5 mm square, and the code is European, ordinary, and all those things are automatically updated. Click on OK. Close.
The automation feature. The automation feature is one of the major advantages of MIDAS FENX. It allows complex geometries to be meshed without requiring partitioning or any other additional efforts, ensuring uniform and smooth meshing with proper node connectivity at the boundaries. FENX Tetra Mesher auto-generates tetrahedral solid mesh with variable sizes in smooth transition. It can include holes, curves, and points that are present in or on the solids, as you can see in the figures shown here. FEA's map mesher generates structured, regular, and orthogonal meshes both on surface and in solids. Moving on to the software.
Meshing of the finite element model. Here we have 3 different meshings required. One is for the girder, the other one is for tendon and for the rebars. First, let's start with meshing of the girder. Go to Mesh, click on 3D from Generate, since it is a solid model. Select objects. So please click on the girder, and I want to give a size of 100 mm mesh size. Coming down, I need tetrahedral meshing. The property is concrete, and the mesh set, I'll give a name of the mesh set as girder. Click on apply. The meshing is being done in the background. Now the meshing is complete. You can see how fine the mesh is, and even at the regions of anchorage block, you can see the meshing is very smooth and uniform. Ensuring perfect nodal connectivity. Likewise, we'll have to mesh the rebars and also the tendons. So let's select the rebars. So for that, let's go to solids, and in solids, I have already hidden the body. Going on to the mesh, we have the girder here. I'll uncheck it. So the mesh is gone, the solid meshing. Now we have the curves. So this one is for the rebars, and this one is for the tendons. Sorry, this one is for the rebars and the other one is for the tendons. So now first I'll hide the rebars. So you can see this will be the tendon, and this will be the anchorage block regions. We have to mesh the tendons as well. So now let's go again to 1D. Select objects. So I'm going to select complete tendons, and the size of the mesh is 10 mm, and the tendon property, the property will be tendon, and the mesh set, I'll give a name as tendon. Click on apply. So the tendons are meshed. Now I'll hide the tendons and activate the rebars. So the rebars are on, and I'll hide the tendons. Going down. So now the tendons are gone. Now let's mesh the rebars. 1D. Select object. I'm going to select the entire tendon, rebars, and the size of the mesh is 10 mm. The property should be rebars, and the mesh set name should be rebars. Click on apply. So this is how we can mesh our finite element model in FENX.
Constraints. Simulation of the global stiffness. Since we are considering only a portion of the structure, in this case just 3 segments, it is essential to apply appropriate boundary conditions that simulate the global stiffness to achieve accurate results. Essentially, we have 2 different approaches. So the first approach is the stiffness at the joints in the global model will be calculated by applying unit loads as shown in the figure. Then point springs will be with the calculated stiffness values will be then modeled at both ends. Rigid links will be used to connect the nodes on the face of the segment to the point springs at both ends. You can refer to the snaps here. Now, the next method is involves importing the global beam model from Civil Index. As you can see the video. So first we'll be importing the global beam element model from Civil NX and replacing the segments under review with 3D geometry model which is imported from CIM within the single FENX model. So now we'll be importing the 3D model from FENX. Now, after meshing the 3D geometry, the beam element joint nodes can be connected to the solid element facing the nodes using rigid links. You can see the snaps here.
Now let's assign the loads, self-weight and pre-stress. For defining the self-weight, go to static analysis, click on self-weight. So in self-weight, you can give the desired name. I'm keeping it as gravity 1. Components Gx, Gy, and Gz -1 direction. That means the vertical direction downward. The load set, I'm going to keep it as load set 1. Click on apply. So now you can see that the self-weight has been applied. Now let's go to the mesh and I can see that the tendons are already selected. I'll click on the body. I'll hide the body. Now the tendons are activated, the mesh set. For defining the tendon pre-stress, go to static analysis. Here you'll find pre-stress. Click on pre-stress. In pre-stress, you can give the design name. I'm going to keep it as pre-stress 1. The element type should be tendon, since these are all tendon elements. Now select objects. I'm going to select the entire tendons, and stress, I'm going to give the stress as 13Y0 at beginning and also at the end. Now the load set, I'm going to keep the load set name as tendon and click on apply. So now you can see that the loads have been applied.
Now, coming on to the final part, analysis results review. First, let's see all the meshing. This will be the rebar meshes that we have created, followed by the girder one and the tendons. Yeah. So we'll check on all the meshes. Let's view the results. Go to the results tab, and we'll go to the final step, and we'll check the one versus stresses. You can see the legend as well. Everything seems perfect, but when you zoom in to the angular block locations, you can find some stress concentrations, which leads to crack. Let's check out the crack status. So in the crack status, it has been observed that few cracks have been generated. On the legend, you can see the crack status, partially open loading and partially open unloading. Fully open cracks can also be seen. So we can conclude that even though the global model is perfectly fine and is giving commendable results, at times detailed local analysis is necessary to find anomalies such as crack propagation. Now, let us briefly summarize the entire webinar. The 3D modeling was completed in CI, where we defined the layout, materials, section properties, tendons, boundary conditions, and the construction stages. The analytical model was then generated by importing the 3D model into CivilNX, where the loads were assigned and activated in different construction stages. The moving load was defined as per Eurocode, and the global model analysis results were reviewed. The design of the PSC section was performed as per Eurocode standards and met all the design criteria. The rebar data was transferred for modeling in CI, and 2D drawing deliverables were generated by linking CIM to CAD ID. For a more localized analysis, 3 segments were imported into MIDAS FENX as solid elements, including the reinforcements and pre-stressing cables, modeled as embedded truss and tendon elements respectively. A non-linear smear crack model was used to study the crack propagation in the segments, while the rebars and tendons were modeled with linear material properties. After the detailed analysis, crack propagation was observed near the anchorage blocks due to the pre-stressing, emphasizing once again the need for detailed analysis. Thus, with M collection package, we can bridge the gap between different entities involved in the analysis and design of a bridge. I hope everyone enjoyed the session. Now let us move on to the Q&A segment.
Okay, now we will move on to the Q&A session. Joseph and Jishan, can you share some of the questions? Oh, I think we're having some technical problems. Can everybody wait for a sec?
Am I audible now?
Yes, you are.
Okay, sorry for the inconvenience. There was some technical issue. So now we shall be taking some of the questions that we had received during the session. So first we'll go with the CIM and the CAD infra design questions. So the first question is, when generating drawings, are drafting parameters such as font type, font size, line spacing, layer setting customizable? So yes, when you're generating the drawings, we can parameterize or we can customize the drawing parameters such as font type, font size, line spacing, etc. So all this customization can be done directly in CAD infra design. So I hope that that question is clear. And the next question that we have received is, can we extract bill of quantities from CIM 3D model? So we can definitely extract the materials or the bill of quantities directly from the CIM 3D model. So you can extract the quantities of concrete, rebar, tendons, and then you can also customize the quantities as per our requirement. So if you want to customize maybe according to the different type of structures or according to the grade of concrete or grade of rebars or the diameters, even that is possible in CIM. So finally, we can extract the quantities directly from the CIM model. And the third question that we have received is, once we make any changes in the 3D model, are the drawings updated automatically? So in CIM, the CIM model and the drawings that are generated using the CAD infra design are directly or dynamically linked. So whenever you make any changes in the 3D model, automatically all the drawings are updated. So this feature is pretty much useful when it comes to the revision part. So these are the major questions that we have received from CIM, and then we have seen that few of the people have raised their hands. So if you could please drop in the questions in the question chat box, we would be able to answer them. Now I would pass on the mic to my colleague Rohit for handling the questions related to Civil Annex and FEA Annex.
Yeah, hello guys. So we have received some of the questions regarding Civil Annex and FEA Annex. The first one is how to model bearings in a curved bridge. So as demonstrated in the webinar, that the bearings have been modeled using the elastic link, and we have defined the stiffness for that. So in that definition, there is an option to use beta angle that we use to rotate the bearings along the curvature of the bridge. So we can rotate that bearings along the curvature. So in that way, we can define the bearings in a curved bridge. So the next question is when to use deformed and original type boundary condition in the construction stage definition. So there are two options in construction stage: deformed and original. So when we have defined some elements in construction stage and that has deformed, and when we are going to the next construction stage and we want to assign our next boundary condition in that deformed stage, then we choose deformed condition. And when we want the boundary condition in the further construction stage in the original point that was there earlier in the previous construction stage, so at that time we use original type. So that can be used in the stage like we have some cable and we are pretensioning that cable, and that has deformed, but we want to apply a boundary condition its original force. In that case, we are again moving it moving it in its original position, so that is causing additional forces in that element. So that is that original that is an example for the original condition. So but for general use, we go for the deformed condition in the construction stage. Now the third one is how can we ensure the mesh connectivity among the solids in FEA Annex. So there are options like in FEA Annex. That first one is the auto connect. So what it does, it connects two different solids, and then when we mesh, it ensures the it generates the mesh for two different solids, and that is connected at each and every generated node. And the other option is the fusion. So we fuse two different solids, and that acts as a single one. And then if we mesh that, so the single mesh is generated for the whole solid assembly. So these are the three major questions that we received. I hope you got the answer for that. And if you guys have any more questions, kindly just put that in the chat box, question box. Just give us a minute. We are just collecting the more questions. Okay, so we have received one question, that is how to model the internal blisters in CIM. So when it comes to modeling the internal blisters, we can use the modeling technique of modeling using the libraries. So what we do is that we would be modeling each blisters as a library, and then later on we would be assigning that particular blister to the major bridge. So that is how you would be able to model the blisters. So it is pretty much easier to model the blister. So in this case, one of the advantages that once you model the blister, you can save it as a separate library, and then you can reuse it for the next project as well. So basically, modeling of blisters is done using the library method. So these were the pretty much questions that we get, and yeah. So if we receive any more questions, we will definitely connect with you via mail, or we can give you the response for that. So now I would like to hand it over to Annabelle for the concluding remarks. Yeah, Annabelle.
Okay, thank you, Joseph and Rohit, for the today's session and the Q&A as well. I'm sure there are more questions from anyone joining this webinar, so you can drop me an email or a message to WhatsApp, and we will try to revert to you on that. Okay, so I also like to thank everyone for joining today's webinar, since it's the busiest of the time of the year. And I hope everyone got the idea of how these 4 softwares in M Collection can be integrated in your course of work. So yeah, thank you everyone. This will be the ending of the session today. Yes, I will see you guys next year with more interesting topics for SEA countries. Thank you for attending today.